Who might have thought it? A notable new review shows that the smooth way might be found someplace totally not the same as previously accepted. As of recently, specialists expected that we are part of the Lanaka system supergroup. Now, another map of the known universe shows something else altogether in position. This would imply that our world is part of a superstructure that challenges generally accepted cosmological models. If we trust the latest discoveries of a review from Germany, our image of the universe might have been off base up until this point. If the new maps of the universe are right, then our world gathering is found someplace totally different than previously expected. Up to this point, our smooth way was identified as part of the Lanaka galaxy group, but now the latest estimations and mappings turn these assumptions upside down. According to this, our smooth way could belong to the much larger Shapley Supercluster. This collection of galaxies is bigger than anything we can imagine. The Shapley Supercluster is one of the largest known structures in the universe, and this mass collection of galaxies is not only overpowering in its sheer size, but also in its difficulty with regard to past cosmological models. The Shapley Supercluster is dependent on similar discoveries as the ancient galaxies found by the James Webb Telescope. They essentially don't fit into the structure of the current cosmological perspective of the Big Bang, the expansion, and the homogeneity of the universe. In a homogeneous universe, structures the size of the Shapley Supercluster shouldn't really exist. The group is also too old to truly support the theory of the prehistoric cosmic detonation. A structure of this size would never have formed in the time that our universe has evidently existed. A tremendous fascination through gravity. Who can imagine the universe as a huge whirlpool? But that's precisely how it seems. As of recently, science liked to draw an image of a straight universe in which objects are evenly distributed, give predictable sizes, and show us a universe in which forces also act equally. However, this image is disintegrating, and the new study from Germany could play a critical role in creating a new cosmology. An international research group, led by the JUMP-NITS Organization for Astronomy in Potsdam, used a novel cosmographic description technique to analyze the movements of 56,000 galaxies. This has resulted in the most state-of-the-art map of the nearby universe, revealing amazing new grandiose designs. On one hand, the study shows an amazing large-scale organization of galaxy superclusters, and on the other hand, the maps again reveal traces of designs and forces that we don't yet fully understand. This map has now also led to a renaming of our galaxy within the newly known universe. The galaxies don't move randomly in the universe. They follow structures, imperceptible flows, and the appealing and shocking power of matter and energy. Large-scale designs, such as the Lanaka system group and the Shapley Supercluster, apply an attractive force through their density and gravity, gathering more and more matter. Researchers refer to such gravitational centers as attractors. Undoubtedly, the giant among the uberstructures is the 1.3 billion light-year-long SLO Great Wall, a collection of endless galaxies, infinite dust, and gas clouds. The mass aggregations of galaxies are voids, massive spaces of vacancy. A strange large-scale structure was discovered in 2017 and named the dipole repeller. This Uber structure, which is also characterized by the absence of matter, literally pushes galaxies away from itself, pushing them toward the great attractors. This creates dynamics that behave like huge sea currents. The smooth way is surrounded by 17 super designs, and each of these designs applies gigantic forces in the universe. The interactions and overlaps of these structures are hard to comprehend, which has complicated the past classification of the specific place of our galaxy. You have to imagine that observing galaxies from Earth is a challenge. Our telescopes need to look through our own galaxy, and then other galaxies overlap the picture. Furthermore, further behind, we find signs of groupings and Uber structures. As of not long ago, it has been hard to accurately predict where our world is situated inside these mass aggregations. The Astronomical Streams 4 study is the latest method to finally give clarity using the most recent AI calculations. Cosmologists initially showed the legitimate movements of the individual galaxies, then they searched for designs that would give further insights about the location and catchment area of the big designs. We can again draw the comparison to sea currents at rivers, for example, between two bodies of land surfaces. These fierce flows can be seen underneath these designs and elements, which should be visible on the surface. There are further water masses, stream channels, and designs that influence the direction of the flow of water. In the astronomical setting, these are the superstructures. The hastily visible developments of galaxies are part of a complex framework where we can currently only begin to expose what's beneath the surface with our scientific possibilities. Our universe is likely the largest sea we can imagine. The interaction of attractors and repellers has only been known for a few years and is similar to the primary discovery of flows within this sea. It is only in the very recent past that we have begun to understand the true dynamics of our universe. The acknowledgement that galaxies move and stream and are part of complex elements is exciting. From one perspective, this situation is energizing, but for researchers, it is also weaknesses. Our science is gradually getting to a place where it needs to give up old cravings to have the option to describe the universe through math and formulas. The universe is turning out to be more and more tumultuous and wild on the enormous scale. Structures and our hypotheses and logical methodologies are slowly falling short. Inside our oceans, we can describe parts, measure water temperatures, notice sea flows, make associations, and make maps. We know that the seas are the water supplies of this planet, and that specific physical principles apply in water, but we can't get a handle on the true nature of a sea, its lavishness, and intricacy with our science. Planning the universe brings shocks. The oldest maps of the universe are 5,000 years and older. Probably the most ancient map of the sky is the Nebra sky disk, which was made by our predecessors thousands of years ago. It shows the sun, the moon, and most likely the Pleiades. Ancient artifacts like this lead us to think about how our predecessors saw the universe and why some stars were so vital to them that they gave them special importance. Today, we have star maps that show billions of stars, and we have very rational methods to reveal the secrets of the universe. However, all things considered, of producing more information, it seems that all new insights are raising even more questions. We also need to anticipate that mistakes in the observations, measurement mistakes, and incomplete data distort their results. Moreover, the observed galaxies are still only a small part of the total mass present in the universe. Galaxies are not even among the best signs of the distribution of matter within these structures because they are turbulent and extremely irregular in themselves. Despite the fact that galaxies show grand mathematical shapes, there are designs and elements within them that can't yet be explained. Even the movements of galaxies are challenging to sort. Notwithstanding their own developments, which are hard to calculate, galaxies are driven away from us by the expansion of the universe, and simultaneously, they attract each other through the force of gravity. Thus, measurements of the speeds of galaxies can be erroneous and uncertain. Astronomers normally use different guides to help them. These are typically compared to one another, and where there are matches, the best probabilities emerge. Where there are significant deviations, however, analysts need to make do with averages. Up to this point, scientists have worked a lot with probability-based values and less with facts while planning our universe, which has made it hard to classify our own world. Due to the most recent calculations, analysts now have the most solid image of the large-scale distribution of matter in the known universe. In spite of these probabilities, Lanaka, the supercluster that scientists thought our Milky Way was part of, ended up being an informative supplement of the much larger Shapley Supercluster. In the new maps, Lanaka may not yet exist as a clear structure. Even more astounding is the way that another megastructure has emerged from the Sloan Great Wall region, which breaks all previous cosmological rules. This mass of a huge number of galaxies and a breadth of around 1,000 trillion cubic light-years shows that our universe should be far bigger than previously expected. The prevailing attractors overload our computers. It has long been no secret that there are huge marks of fascination and shock in our universe. Yet, what has remained relatively obscure so far is the justification for the presence of these forces. The three-dimensional models, which show the flows and gravitational superstructures in the local universe with remarkable accuracy, should give insights into the dynamics. We should draw a comparison with the sea again. Imagine that we are truly inside a vast sea with what we know as our universe, and that this sea is a part of a world. Then, we can't preclude the possibility that we are currently just investigating a straight line and erroneously assuming that it represents the whole universe. We could also find structures within the universe that would correspond to what might occur if we suddenly encountered expanses of land in a natural sea. The 17 large gravitational wells identified so far in our cosmic area could be interpreted as anomalies on the seafloor, which then favor certain directions of water flow. The Sloan Great Wall may be something like a stretch of ocean, and the smaller designs are areas within that ocean. The impacts of the Sloan Great Wall are over 2 times as extensive as those of the second biggest attractor, the Shapley Supercluster. Lanaka was and is a fairly small area inside this ocean. The impacts of the bigger attractors, like Shapley, Hercules, and the Sloan Great Wall, push analysts and our computers to the edge of the data field. They essentially surpass our abilities and imagination. It's a bit like trying to make predictions about the impact of the whole Pacific on the bank of Hawaii, around 1 meter beneath the water surface somewhere in the Polynesian Ocean. We simply don't have the means to see these regions and accordingly place them accurately. Although the new study from Potsdam has already given remarkable new insights, we will need significantly more exact computations and maps in the future. All predictions are currently nailed to the ESA's fresh-out-of-the-box new Euclid telescope, which is now undertaking a fundamentally superior mapping of the sky. The Vera Rubin Observatory is also expected to provide the most reliable ongoing sweeps of the universe in the near future, and quantum computers may soon fill the gap in our understanding of the universe. Press that subscribe button now. The best discoveries are yet to come.